example 15.6. Again, conservation of momentum. And in these last couple of examples, we see how we combine conservation of energy with conservation of momentum. In the previous one, we had two cars coming at each other, and then they collided, and then they rebounded with no energy lost, and we were able to use the conservation of energy as well to solve the problem. In this case, it's slightly different, but anyways, the point is you need to learn how to use the different principles together. Okay, so we'll see how in this case we use it during a collision. This case we use conservation of energy before collision. Okay, we'll see how that works. So we have a rigid pile. Okay, these things are piles. Okay, these things over here. I presume that they are for kind of a foundation for a building. And the idea is that you've got these concrete piles and you want to drive them deeply into the sand so that they can, I guess, help you with your foundation. I'm not a civil engineer, but that is kind of the idea. So now how are you going to drive this pile, this massive concrete peg into the sand? Well, you're going to drop a hammer. So this thing is, in this problem, is 800 kilograms. This hammer is 300 kilograms. All right? So the pile is driven into the ground using the hammer. The hammer falls from rest at a height of 0.5 meters. Okay, half a meter, and strikes the top of the pile. Okay? Now listen, determine the impulse which the pile exerts on the hammer if the pile, this is the pile, is surrounded entirely by loose sand, so that after striking, the hammer does not rebound. Okay, so it hits the pile and then they move together. So they start off as separate particles at state 1, then at state 2, after the collision, they move into the sand together. Okay? Now, what we need, let's just jump to the money, like I always say. Okay, so I think I identify that this is going to be a conservation of momentum problem. Why is that? Because when they collide, these impulses, let's call it R minus R, these impulses are internal to the system and they cancel out. Okay? They cancel out. So, but now you may say to me, okay, but hold on. We've also got the impulse due to the weight of the hammer and the pile. Okay? And we've got the impulse due to the sand resisting the pile. Okay, so all of these. Okay, let's just back up. What are impulses? Impulses is basically a force times time. Okay, so we need to look at the free body diagram. So during collision, you've got this very large, these large forces. Do they use R here? Okay, so R is the force. Okay, R is the force of the impact, these impulses between the hammer and the pile. But we've also got forces due to weight of both the hammer and the pile, and we've got the resistance force of the sand. Now this is where we need to understand what are impulsive, okay, and non-impulsive forces. Impulsive forces. Okay, so these are the impulsive forces, meaning they are extremely large in relation to non-impulsive forces. What are non-impulsive forces? They are forces that do exist, they do cause impulses, but they are so small in relation to, say, this R and minus R, that we can basically neglect them. Okay? Maybe in another video I'll do an illustration of a tennis racket and a tennis ball. Basically, if you've got a tennis ball about to hit, well, no. If you've got the tennis racket, okay, imagine that that's a tennis racket. Use your imagination. Okay, there's the tennis racket, and it hits the tennis ball. The tennis ball has a weight. I think I need to go and look at the at my information, but say of 0.5 Newton, something to that effect. Whereas the impulse between the tennis ball and the tennis racket was something like 350 Newton second, something like this. So I may get my calculations slightly wrong here, or my numbers slightly wrong. But you see, the idea is that the impulse between the ball and the racket is 350, whereas the impulse due to the weight is half a Newton second. So you can see 10, 20, almost 100 times, well, just less than 100 times larger. Okay? If this was 500, it would be 100 times larger. But can you see the idea? This is a non-impulsive force, and this impulse between the tennis ball and the tennis racket is an impulsive force. Okay, so these are then considered let's just check, the weights of the hammer, the pile, and the resistance force are non-impulsive. Okay, we can ignore them. All right. The impulsive force R is internal to the system and then therefore cancels. Okay, I've mentioned that. Okay, so now that we've decided, we've analyzed the problem, we can then go and see if we can solve it using the conservation of momentum. But now you say to me, but hold on, why are you skipping this section? The reason I'm skipping this section is because I always go for the money first. I try to see if I can solve it. I know that this is a conservation of momentum problem, so I go straight to my conservation of momentum equation and I see if I can solve it. Okay? And we have the momentum of this plus the momentum of this at state 1 must equal the momentum of this and this at state 2. Okay, so I've got the mass of the hammer, but I don't have the velocity of the hammer at impact, right before impact. Okay, I've got the mass of the pile, and I do have the velocity of the pile at impact, which is 0. The point is, I go straight to this equation, and then I see, oh, I don't have the velocity of the hammer just before impact. So what do I need to do? Now I need to collaborate with other ideas, such as the conservation of energy. And how do we use this? Well, we know that this thing drops a certain height, which is 0.5, and we can use T1 plus T2, T1 plus V1 is T2 plus V2, or T0 plus V0 is T1 plus V1. Conservation of energy. Okay, so we've got our initial kinetic energy is 0 because the velocity at the top was 0, right? At that height it was 0. Then we let it fall. Okay, and the potential energy at the height was mgh. There's the potential energy. There's no potential energy due to spring. So at this height, we've got this situation there. Then it falls down, and it impacts. Okay, and we've got half mv of the hammer squared, and then we have 0 potential energy, and we are able to then calculate the velocity just before impact, which is 3.13. Now I can take that and I can put that in there. Okay? And on the right hand side we've got, remember, these impact, they collide and then they move together. So you could write this as follows: 800 plus 300 V2. Okay, and then you can solve for your V2. So now we've got the velocity of both of these, the entire system moving together at state 2. But the question was also, what is the impulse which the pile exerts on the hammer? What is the impulse which the pile exerts on the hammer? So as you can see, using this technique here, we don't know what the impulse is, because if we consider both particles as our system, then the impulse between the two is cancelled out. So what do we need to do? We need to just isolate one of them. You can use either that one or either the hammer or the pile. Both will allow you to calculate the correct answer. So if we consider the hammer, then we've got mv at state 1, just before impact. Okay, then we've got this negative impulse, minus rdt, is equal to mv2, the mass of the hammer times the velocity. And there we can calculate our impulse. Take note that because we chose the hammer, the impulse is up, and so we've got a negative impulse. If we choose down as positive, down is positive. Whereas if you chose the pile, then you're going to have R acting down, so you would have a zero initial momentum, because velocity would be 0, plus R dt is equal to 800 V2, and V2 is 0.85, and you should get the same answer. Okay guys, cheers.